So Unit 8, normal calculations. Well, what we've done so far is we've looked at distributions of data where the data is grouped around a mean and there's a standard deviation associated with that data. And what we're going to do in this unit is learn how to compare one set of data to another set of data and sort of transforming the mean and the standard deviation of one set of data and maybe one or more other sets of data to a standard so we can directly compare apples with apples. First, though, with the normal calculations, there's a summary of the video. And one of the things I just want to talk about very briefly is, so if you have a distribution, and in this case, height of American women, you'll see that in this graphic, we're told that 68% of the information is between -1 standard deviations and +1 standard deviations from the mean. And here's the mean right here, down the middle. What that means is that 34% of the height of American women between the mean and 1 standard deviation lies between the mean and 1 standard deviation, and 34% of the data lies below the mean and 1 standard deviation below the mean. But in total, between 1 standard deviation below the mean and 1 standard deviation above the mean, there's 68% of the data there. Now, if we go out 2 standard deviations from the mean, again, here's the mean, 2 standard deviations from the mean, you've got 95% of the data collected between 2 standard deviations below the mean and 2 standard deviations above the mean. Well, half of 95 is 47.5. So that means that 47.5% of the data lies between the mean and 2 standard deviations above the mean, and 47.5% of the data lies between the mean and 2 standard deviations below the mean. Now, there are different forms of Z tables that are in use. There are also ZScore calculators that one can access online. The ZScore table that's in the video is not what I want to use. Here's what I want to use. I want to use this ZScore table. This ZScore table is actually found in your textbook that you use for 047 math. And if you want to read extra material about statistics or probability, take a look in the textbook that you have for that first part of the course. Now, the thing to recognize with this particular type of ZScore table, all of these Z-scores are referenced on the mean. And so if the mean is at 0, the Z-score is above the mean. Now, the Z-score, really what it turns out to be is just like a fractional standard deviation. So here, I'll just show you something. On this table, if I find 1 standard deviation above the mean, I go down the table. Here we go. 1 standard deviation above the mean. It's right here. And that's 34.1% of the data. So that means at 1 standard deviation above the mean, 34.1% of the data is between the mean and 1 standard deviation above the mean. Now, earlier and in the video, it says approximately 68% between -1 and +1. So that's 68 is 34. But this is precise. 34.1% of the information is located between the mean and 1 standard deviation above the mean. So looking at the graphic on this table, what we're saying is if this is Z equals 1 here, there's 1 standard deviation above the mean. Z equals 1, 34% of the data is between the mean and Z equals 1. So what we want to be able to do is compare 2 normal density curves. And the way we do that is by calculating a Z-score, and that just standardizes the curves. You can see that 99.7% of the data is between 3 standard deviations below the mean and 3 standard deviations above the mean. And so from the shape of the curve, you can see that there's just very, very little data either above 3 standard deviations above the mean or below 3 standard deviations below the mean. This is the equation we're going to use to calculate Z-scores, standardized value. So in this table, what we have is X is the value, mu is the mean of the distribution, and sigma is the standard deviation. By calculating a Z-score, we transform the horizontal scale of our distribution to a Z-score, so we can compare one distribution to the next. Don't do the unit activity. What I want you to do are the exercises and the follow-up questions. So in the exercises, I've got some questions. So here, distribution of heights of young women 18 to 24 years old is approximately normal with a mean of 65.5 inches and a standard deviation of 2.5 inches. So we want to find out, what two values to the heights of the central 95% of young women lie between. And then draw a normal curve. Well, the mean is 65.5 inches, which means that, well, if the standard deviation is 2.5 inches, that's one standard deviation. Two standard deviations is going to be 2 times 2.5 inches, which is 5.0 inches. So now, because if we're looking for what two values 95% of the height data lies between, 95% of the data will lie between 2 standard deviations above the mean and 2 standard deviations below the mean. So what I've got to calculate is below the mean and above the mean. Okay, so below the mean, 65.5 minus 5 is 60.5 inches. And above the mean would be 65.5 plus 5, which is 70.5 inches. So 95% of the data will lie between 2 standard deviations below the mean. This is 2 standard deviations below the mean, and this is 2 standard deviations above the mean. Now I'm going to try to sketch this graph. So to sketch it, I'm just going to do it freehand. And here's the mean, and the mean value is 65.5. So one standard deviation, here's an inflection point. That's plus 1, that's minus 1, and then plus 2, and minus 2 would be there. So if I was to sketch this in, all this data is between 2 standard deviations above and below the mean. So this is 95% of the data. So 95% of American women have heights between 60.5 inches and 70.5 inches. All right, based on the 68, 95, 99.7%, we'll explain why only 2.5% of young women are more than 2 standard deviations taller than the mean. Well, if you recall, this shaded portion represents 95% of the data. This is 95% right there, all the information. So 95% taken away from 100% is 5%. So that means down at the bottom end, down here, you've got, well, half of 5%, which is 2.5%. And at the top end, above 2 standard deviations above the mean, you've got 2.5%. So now this all adds up to 100%. 2.5 and 2.5 is 5, and 95 makes 100. So only 2.5% of American women are taller than 2 standard deviations above the mean. But likewise, 2.5% of American women are shorter than 2 standard deviations below the mean. There we go. What is the Z-score for a 20-year-old woman who is 6 feet tall? And interpret this value. So in order to calculate the Z-score, we need to have the formula, which is Z equals the value minus the mean divided by the standard deviation. Okay, so I've got to pick some information out here. So X is the value, so 6 feet. X equals 6 feet. Well, there's 12 inches in a foot. So 6 feet is 6 times 12, which is 72 inches. That's our value. And now we need to get the mean and the standard deviation. So let's take a look at the question. The mean is 65.5 and the standard deviation is 2.5. So now I'm going to calculate the Z-score. So Z equals 72 minus 65.5 divided by 2.5. So Z equals 2.6. Well, what I'm going to do now is I'm going to look at my Z table. So Z is 2.60, 0, in fact. Here we go. I go to the Z table and 2.60. Let's see. Well, different columns here. Here's Z. There's 2.8, 2. Oh, we're coming along. Oh, 2.6. Here's Z equals 2.6, and that's a percentage of 43.5%. Now that's 43.5% above the mean. There are a couple of ways to interpret this. What I would say, this woman is 6 feet tall, and let's find out how what percentage she is taller than the rest of the American female population in that age group. So I'm going to draw a distribution, just a rough sketch. I'm going to locate the mean. The mean was 65.5. Her value is 72. It's out there. So here's 2 standard deviations above the mean. Here. So that's the mean, and that's 2 standard deviations above the mean. Where this woman is, she's 2.6 standard deviations above the mean. So she's in this. There's a cutoff right there. That's 2.60 standard deviations above the mean. Well, that means from her Z-score, she's taller than 43.5% of the females above the mean value. So I'm going to shade that in carefully. And so this is 43.5% of the females above the mean. Well, that's interesting, but we want to say find out how much, like what percentage is she taller than the American female population with this age group. Well, it turns out that this value is 43.5% female population. It also turns out that exactly 50% of the female population is below the mean. Doesn't matter how many standard deviations you go below the mean, it's 50%. So now I can say that this 6 foot tall woman, the 6 foot tall woman is 43.5% plus 50.0% is 93.5% taller. She's taller than 93.5% of the American woman. 93.5% taller than the other American woman in the group. Another way I could look at this is she's in the top 6.5% in terms of height. Okay, two national college entrance exams, the SAT and the ACT. So the first question is, what percent of all SAT scores are above 600? Explain how you arrive at your answer. Well, what I'm going to do is I am going to calculate a Z-score for the SAT scores with a value of 600. So here we go. So my value is 600. The mean is 500, and the standard deviation is 100. So I want to find a Z value or a Z-score. So that's going to be equal to the value, take away the mean, and divide it by the standard deviation. Notice that with this formula, you can actually have negative Z-scores. And if you get a negative Z-score, that just means the value is cost less than 0, so it's below the mean. In this case, however, we've got a positive Z value because the value 600 is greater than the mean. So Z equals 600 minus 500 divided by 100. Well, that's 100 divided by 100. Well, that's just 1.00. So that means that if Z is 1.00, 34.1% of the scores are between the mean and Z equals 1. Let me draw a picture. The question, however, is how many are above 600? The way to answer this is really draw a picture. Always draw a sketch when you're dealing with Z scores. It's my advice. Okay, so here's our mean. The mean is, change color, the mean is 500. Standard deviation is 100. So that's 0, that's plus 1. What this means is that 34.1% of the scores between 500 and 600 looking at my picture, so this is 34.1%. How do I know that? I'm going to look on my Z table. I'm going to find a value of Z if Z equals 1. I'll go for that. Find Z equals 1. Oh, there it is there. When Z is equal to 1, the percentage is 34.1%. So 34.1% of the scores lie between the mean and 600. But also, here's the thing, 50% of the scores lie below the mean. Okay, so that's 50%. So how many scores lie below 600? Well, scores less than 600, or if you remember your inequality signs, scores less than 600 will be 50% plus 34.1%. So 50.0 and 34.1 is 84.1% of the scores are below 600. But that's not really what we were being asked. We were being asked how many scores are above 600. So that's this part of the curve in here. These are all the ones above 600. Well, what I'm going to do is scores greater than 600. Okay, scores greater than 600. Well, that's going to be equal to, that's going to be 100% minus 84.1%. The 84.1%, these are the scores, 84.1% of the scores are below one standard deviation above the mean. You've got all 50% between the mean and like way out, negative 10 standard deviations. And the values between the mean and standard deviation of +1. Why +1? Because when I calculated a Z-score, I came up with a Z-score of 1 for the value 600. So that means 100% minus 84.1% will be equal to the number of SAT scores greater than 600. Well, that's 15.9%. So the next question, we're going to be using the concept of the Z value or Z score to compare two different values that were generated from two different distributions, an SAT score and an ACT score. So what I need in order to do this comparison is I need to know the values, like the values of the scores. I also need to know the mean of the SAT distribution, the mean of the ACT distribution. I also need to know the standard deviation of the SAT distribution, and I need. So for the SAT, the mean is 500, standard deviation is 100. For the ACT, the mean is 18, standard deviation is 6. Now I'm going to calculate Z scores for both of these individuals, so we can compare to see who's actually scored really higher, assuming that both tests are equally difficult. I've got the information to calculate Z score for this person who wrote the SAT, and I have the information in the Z score formula for the person who wrote the ACT. Now I calculate the scores. Well, the SAT score, the one in red, is results in a Z of 1.3. The ACT score, which is in green, results in a Z score of 0.667. Now, both Z scores will result in, or they're both positive, so they're both above the mean. So based on Z score, the student who wrote the SAT test has performed better than the student who wrote the ACT test, because the Z score for the SAT student is larger. They're further along. Let me just draw a picture. So looking at the distribution curve, the student who wrote the SAT had a Z score of 1.3, which is more to the right of the mean, and they've done better than a larger percentage of the student population who wrote these tests than the person who wrote the ACT and got 0.667. Let's just calculate what percentage these students did better than the average. Looking at a Z table, the student who got a Z score of 1.3 did better than 43.5% of the people above the mean. The person who got a Z score of 0.67 did better than 24.9% of the average students. So you've got a question about, it's just distribution of selling price of houses in a city close to normal. Well, think about Vancouver. You've got they got an answer in the back of in your solutions manual, but basically, distribution of house selling prices in Vancouver would probably be something like this. Up here, you've got these uber expensive houses, and you got some very expensive houses, moderately priced houses. In Vancouver, there's no such thing as a cheap house really. So your distribution is really skewed. And because it's a skewed distribution like this, you can't apply the it's not a normal distribution. You cannot apply the 68, 95, 99.7% rule. So I want to find what percentage of values are less than z of minus 1. So I'm going to begin by sketching a distribution curve. There's 0, and there's minus 1. Now, when I look up the value of z minus 1 on a z table, I am going to determine the percentage of scores between the mean, 0, and minus 1. So this isn't the percentage of scores less than z minus 1. This is percentage of scores between 0 and minus 1. So let's just figure out, discover what is the value, what value when z equals minus 1, what percentage of scores lie between 0 and minus 1. So when z is 1, 34.1% of the scores lie between 0 and 1. But this is symmetrical. So if you've got a z-score of minus 1 over here, well, that means that 34.1% of the scores are between 0 and minus 1. If you've got a z value of plus 1, 34.1% of the scores, the values are between z equals 0 and 1. So this is why it's important to draw the picture so you can figure out to help visualize what's going on here. So back to the question, 34.1% of the values are between 0 and minus 1, between the mean and z equals minus 1. Well, the question is, what percentage is less than minus 1? Well, 50% of the values are less than the mean. 50% of the values are more than the mean. So since 50% of the values are less than the mean, if I subtract off the values between 0 and minus 1 from all the values that lie basically between negative infinity and 0, I'll figure out this portion of the curve here. So once again, everything below 0 is 50% of the data, the information. So what I'm going to do is I'm going to say, okay, well, everything from 0 out to here, that's 50% of the data. What I'm going to do is I'm going to subtract off that to get the difference, which is this, the percentage of the data below z equals 1. So here we go. So percentage of data where z is less than 1 will be 50.0% minus 34.1%. Well, what's that equal to? That's equal to 15.9%. So 15.9% of the data is less than z equals, or is less than z of minus 1. So if you want to find out what percentage of values in the sample are have a z-score greater than 2.25, you look up a z-score of 2.25 on a z table, and you see that a z of 2.25 means that there's 48.8% of the data is above the mean. So when you do a sketch of your distribution, 0 being the mean, z-score is 0, 48.8% of the data is above the mean. Now, since in total, 50% of the data is above the mean. The difference between the 50% of the data above the mean and the 48.8% of the data corresponding to a Z-score 2.25 above the mean, that difference is 1.2%. So that means that 1.2% of the data is actually greater than a Z-score of 2.25. So now we're asked to find what percent of the data is between a Z value of -1 here and a Z value of plus 2.25 in here. So what you need to do is you're going to add the percentage of values between 0 and Z of -1 to the percentage of values between 0 and 2.25. Let's get the percentages. So 34.1% of the data is between 0 and -1. That's 34.1% of the data. And 48.8% of the data is between 0 and 2.25. That equals 2.25. So I'm going to add these two percentages together to answer the question. So this is going to be equal to 34.1% plus 48.8%. So that's equal to 82.9% of the data is between a Z of -1 and a Z of plus 2.25. So now it's time for you to do the review questions. Just remember that when you're working with Z values, just always ask yourself, okay, what is the mean? What is the standard deviation? And what am I being asked to compare?